Good day, I'm Dmitrii. I'm a software engineer and STO lead. Today we will discuss how to move from best practice to a systematic tuning approach based on a specific workload. DBMS is a critical component of data-intensive application. Their performance is often measured by throughput, how fast the system can ingest the new data, and latency, how quickly it can answer queries. Achieving high performance in DBMS is hard because the systems are complex and expose many tunable parameters. As databases and applications grow in size and complexity, it becomes increasingly difficult to manually configure DBMS to meet requirements. The right configuration depends on many iterative factors: workload, data, hardware, and version. And it's difficult to account for all of them without automation. Most DBMS after tuning tools check each DBMS instance independently, and therefore cannot apply knowledge from previous tuning attempts. This is inefficiently because each tuning attempt can be time-consuming and resource-intensive. Universal best practice often make things worse because systems start with different baseline workload. What speeds up some workload can harm other. A manual trial and error approach is tedious, costly, and inefficient because many parameters are independent. The DBMS tuning guide strongly suggests that a DBA only change one parameter at a time. This is wise but woefully slow given the large number of variables. It's also not entirely helpful because changing one parameter may affect the benefits of another. The different combination of knobs settings means that finding the optimal configuration is in hard. Some parameters have continuous ranges. There are many possible settings for knobs, and the difference in performance from one setting to the next could be irregular. One often cannot reuse the same configuration from one application in another. Therefore, that a DBA spends of tuning one DBMS does not make tuning the next one any easier. This is because the best configuration for one application may not be the best for another. Databases continuously add new parameters. Complex monitoring solutions are required. The above problems show how difficult it is to configure databases. This complexity is a major factor contributing to the high total cost of ownership of the database system. To reduce the manual tuning efforts of DBA, state-of-the-art approaches automate the variable tuning via machine learning techniques. This ML-based tuning system follows the main concept of trial and error to exploit the configuration space iteratively, balancing between the exploration of unseen regions and the explorations of known space. While this tuning system possesses the potential to reach well-performing knob configuration, eventually they still occur significant tuning cost. Such high tuning costs stem from the inefficiency in handling two difficulties: the larger number of knobs that require tuning, the wide search space of possible value for each knob. DBAs often rely on domain knowledge for tuning. External domain knowledge directly reveals tuning hints, including the important knobs and typical value ranges for each knob. To solve the above problems, it was decided to perform an experiment of LLM tuning of the DBMS configuration with the reuse of training data collected during previous tuning stage. The idea is to select most important metrics that characterize a given workload type Map previously unseen database workload to known workloads so we can transfer prior experience and recommend new DBMS configurations using LLM that leverage domain knowledge to improve the optimization process. Reusing prior experience together with LLMs reduce the time and the resources needed to tune a DBMS for a new application, since LLM can propose new parameter sets based on current knowledge of good configurations while still exploring new value. In this experiment, we have implemented a database tuning system that uses data collected from previous tuning stage to select important metrics, map the target DBMS workload, and tune configuration using an LLM. Each recommendation adds information to a feedback loop that improves the models and their precision. The system has two components. Agent interacts with the target DBMS, collects runtime metrics, applies new configurations, and gathers performance metrics. Tuning platform receives the agent's data and stores it alongside prior tuning data. It's run background processes that continuously analyze new data and refine internal models. These models identify relevant parameters and the metrics without human intervention and define the repository workload similar to the target. Based on this information, the LLM computes the next configuration to the agent to apply. After each metrics collection period, two steps determine which configuration to recommend. First, the platform maps the target workload to most similar workload with the same DBMS profile and hardware recorded in the past. Once the tuning platform has found the best match using the collect data, it moves on the second step, where it recommends a configuration of parameter specifically designed to improve the target metrics for the current workload, DBMS and hardware. To map the target workload, the first step of the tuning system is to find a model that best captures the distinctive characteristics of the target workload so it can identify which previously observed workloads are similar. This allows the information collected in previous tuning session to be used to find a suitable configuration of parameters for the new application. The best approach is to use DBMS runtime internal metrics to characterize workload behavior. All modern DBMSs provide a lot of information about the system. For example, MySQL in a DB engine reports statistics on page read-write, query cache usage, and log overhead. These metrics provide a more precise view of the workload because they cover more aspects of runtime behavior and depend directly on the DBMS configuration. The next step is to automatically remove redundant metrics. It's important to prune them so the platform only considers a minimal set that captures performance, variability, and distinctive workload characteristics. Redundant DBMS metrics arise for the two reasons: different levels of detail for the same metrics. For example, MySQL reports read volume in bytes and in pages, and the metrics for different DBMS components whose values are highly correlated. We use two well studies. First, factor analysis reduces the high-dimensional DBMS metric space and to a low-dimensional representation, improving the reliability and quality of clustering. Then we apply commits to cluster the low-dimensional data into meaningful groups. We keep one representative metrics per cluster the one closest to the centroid. This cluster corresponds to distinct aspects of DBMS performance. The next step in the experiment is to map the target DBMS workload to the most similar workload in the repository based on performance measurement for the select metric groups. We use a dynamic mapping schema because the matched workload tends to vary during the first few experiments before converging to a single one. The workload mapping calculations are simple. They perform computers the Euclidean distance between the target workload's metric vector and the corresponding vector for each repository workload for each selected metrics. Finally, it computes a score for each workload by averaging this distance across all metrics and chooses the workload with the lowest score and the closest to the target workload for the given observation period. To solve the problem of tuning MySQL configuration, we have implemented a pipeline based on the large language model. Natural language processing has advanced significantly with large language models, which have proven effective across a wide range of tasks. Their impact extends beyond natural language processing into the database development community, where there is search of LLM adopts to improve the DBMS. For example, data profiling, code generation, table query answer. There are three common ways to use LLM: train from scratch, fine-tune an existing model, and use a pre-training model without changing its parameters. They are first to require large amounts of resource, compute and training data. Given OpenAI's in-context learning capability, we chose option 3 and use OpenAI as a default model. This stage, we determine which configuration variables have a significant impact on DBMS and performance and tune only these important parameters. Existing models rely on ML-based important selection and require hundreds or thousands of DBMS evaluations across workload and configurations. In contrast, DBAs consult guides to choose which parameter to tune for better performance. We therefore prompt the LLM to emulate a DBMS empirical judgment to achieve a workload-aware approach that does not require training. The algorithm selects its important parameters at three levels. System level. Given the workload version, identified parameters now they strongly influence performance. Workload level. Provide the LLM with the workload type and target optimization metric, throughput or latency, to refine the parameter selection. Dependency level. Given the already selected parameters, use the LLM to add independent configuration variables. To generate a new configuration, the LLM resaves the set of important metrics and variables values for each known configuration in the repository for the target server and the closest selected workload, and constraints DBMS version, ACID, memory, I/O limits. We also pass the previously selected list of important variables with their ranges to prevent fantasies, and the target optimization metrics that needs to be improved. The model outputs strictly formatted JSON with 1 to 3 candidate configurations, including expected impact on the objective risk assessment and resource effects. Each candidate that undergoes post-checks for the DBMS version compatibility and the target server's resources. We estimated each candidate's utility expected improvement and chose the next configuration with the maximum improvement in the target metric. After initialization, the LLM works iteratively. Select the next configuration by maximizing the evaluation function evaluates the configuration in the DBMS, update the model with a new observation. Each experiment enriches the workload catalog and improves subsequent recommendation. As discussed, the platform needs datasets that cover varied combinations of configuration variables. Other ways, each tuning session becomes a first-time application, and the platform cannot reuse prior knowledge. This means we must see the repository with Intel data. For these experiments, we use bench-based workloads that differ in complexity and system requirements. We also evaluate device variable configuration. For each workload, we perform parameter tuning using random values. Some generated configuration are skipped because the DBMS refused to start when a parameter exceeds the machine's physical capacity, buffer pool size larger than RAM. In each trial, we collected both external metrics, throughput latency, and internal metrics, page read, page write, from the DBMS. We have performed an experiment in tuning DBMS variable configuration by using training data collected during previous tuning session. This approach combines mathematical models and LLMs to remove redundant metrics, map previously unknown database workload to known workloads, identify important variables, and recommend configuration parameter. Using a workload-based approach provides the LLM with a set of knowledge about the impact of parameter, value of metrics, and targets. It enables the reuse of parameter settings and repeat searches for near optimal configuration. As shown, the system finds the most efficient configuration within 20 iterations, quickly achieving a significant performance improvement at 54% low latency. Thank you for your attention.